Hello everybody, we're going to take care of some notes that we had from last Friday. We didn't finish through everything. We kind of talked about this information, but we just need to go a little bit more in depth. So starting off discussing the benefits of machines. We discussed this, we had a bell ringer question about this. Essentially they make the amount of force that we have to do less. So they take our force and multiply it, and that is how we get mechanical advantage. Okay, so most machines are a combination of several simple machines. As we kind of have below here, we have the lever and incline plane are a couple of the simplest ones. So you can see the examples here. The ideal mechanical advantages are listed with these. If you ever need these, then I would give them to you. However, this is your, remember when we're working with mechanical advantages, you have your effort amount, and then you have your resistance amount. So here we have an effort lever and a resistance lever. So you can see the box is on the resistance lever, and then our actual lever, our effort lever, is this right hand side. And the fulcrum is also needed for a lever because you have to have some kind of a pivot point on a lever. And generally your effort lever is going to be the longer of the two, otherwise it would kind of defeat the purpose of using a lever. For an inclined plane over here, you can see your ideal mechanical advantage is just the length over the height. Okay, it's going to take that amount of force that you have to apply, and it's going to take it times the sine of whatever angle you got there and reduce it. Okay, so that's how an inclined plane works. And a couple other ones that we have down below. We'll do a lab on one of these. But a pulley system, the ideal mechanical advantage is tied to the number of ropes supporting the object. Okay, and so that could be dependent on how many pulleys you have there. So we could have another pulley in here, and then you're going to have a few more ropes going between the objects. So if I have the way it is here, I have one rope and two ropes. If I put another pulley in there, then I'll probably have three ropes. And then another one over here is the wheel and axle. So the wheel and axle depends on if you're applying the force on the axle or if you're applying a force on the wheel. Okay. In this scenario, we have a rope around the wheel, and so the wheel will be our effort radius, or effort force is going to be applied on the wheel, and then the axle is going to be the resistance radius, because the axle is going to be what's doing our work for us. Okay, so these are going to be more important, that we need to identify what the effort force is and what the resistance force is. In this scenario, I guess it's always effort over resistance, but in this scenario the effort is the wheel and the resistance for radius is the axle. A couple other ones that are kind of deemed simple machines, now they might not seem as simple, would be a wedge and screw. And I had a discussion previously with the last physics class why these are classified as simple machines, because if you see this one, we can kind of split a wedge in half, and we have an inclined plane here and an inclined plane here. So really a wedge is two inclined planes. And same kind of idea for a screw. It's kind of like a wheel and axle with an inclined plane wrapped around it. So those are just a bunch of little inclined planes there. The reason these are still classified as simple machines is just because that's the way they did it during the Renaissance, and they adopted a lot of information for physics during the Renaissance, and they haven't declassified them, and so that's just kind of maintained since then. But it also deals with the way that they change force. So this one is a simple downward force. It changes our direction, the direction of our force just one time here. It's a downward force that applies an outward force, because that wedge is going to split things apart. It's going to separate. It's going to be perpendicular to the force that it's applying. And a screw takes a rotational force, or a torque, and that applies a downward force here. Okay, so it's just changing the force, the direction of the force one time. So that could be another argument for the simple machines there. And your ideal mechanical advantage of the screw is the is 2 pi r, so it's the circumference over the distance between each of the little inclined planes per se. So I have some equations written here for you. We wrote these down the other day. You want to make sure that you have these in your notes for the next examples here that we're going to be working through. Okay, so we have our mechanical advantage is your resistance force over your effort force. Okay, and again, this kind of depends on what scenario you're looking at. So this one I have it as output force over input force. I think that was dependent on, well, actually the resistance force is the output force. Okay, so whatever force you're getting out from the force that you're putting in. So our effort force is the input force, and resistance force is the output force. Ideal mechanical advantage is your effort or your effort distance over your resistance distance. Sounds kind of goofy, but how many centimeters or meters are you covering, and how many centimeters or meters is the machine doing the work for you? Also, this could be going along with a radius. We have effort radius over resistance radius, so that's another one that can go with that. And then down here we have our efficiency. This part right here is not 100% necessary if you change your efficiency as a percentage or as a decimal. So say we have a 95% efficiency. When you put that, or I'm used to putting it into the formula is 0.95. And if you do that, this is unnecessary. Okay, the formula is set up so you put this value in there and then divide it by 100. But just understand that I'm probably going to be doing it this way where the 100 is already gone. So that's the way I'm going to be using that. So, done with simple machines, we got to talk about compound machines. So it's 2 or more simple machines, and they're linked in such a way that the resistance force of one machine becomes the effort force of the second machine. Okay, so they're kind of connected where we'll have something like this, where we'll have effort force or effort radius over the resistance radius is going to be multiplied by the effort force of the second part, kind of like this, where this becomes that piece right there. The resistance of one value becomes the effort of the other value. Okay, and we'll see that with a bicycle example here in a second. So if you consider a bicycle example, the pedal and the front gear, okay, pedal and front gear are your wheel and axle. And that's connected to the bike chain, which is connected to the rear gear and the rear wheel. Okay, so those are all connected. So in order for us to calculate the mechanical advantage of something like this, where it's a compound machine, you need to take the mechanical advantages of all of the simple machines and multiply them together. So it'd be, you identify, say for example, the bicyclist is pedaling on the bicycle. So mechanical advantage 1 would be the pedals and the gear. And then mechanical advantage 2 would be the rear wheel and the rear gear. Because that's what is making the bicycle go. So we'd have to multiply those 2 values to get the mechanical advantage of the bicycle. Okay, and so here's a diagram for you. Usually when we figure out mechanical advantage, we go from the pedal being pushed at a 90 degrees. We just kind of go from the optimal situation, because if you don't do that, then we all know that it's not as optimal, and so we usually calculate mechanical advantage from the most optimal standpoint. Okay, so here we would have the, I guess we can kind of make our mechanical advantage here. So we have our input on the pedal. It's going to get, the force on the pedal is going to be compared to the force on the gear. Okay, and then that, if we're talking about forces here, so the force on the chain, so the force on the chain is going to be the force on the rear gear. That's our effort force there, which would be the force on the ground or the rear. I know this is kind of hard to read. Rear wheel. And so we can kind of compare these two. we can take these two and match them up, because that's usually information that we're given. So you could take the force on the rear gear and divide that by the force on the front gear. And generally this isn't forces, it's usually radiuses or radii. So you take the rear radius divided by the front radius for the bicycle here. Okay, and we can also kind of think about, I wrote this once already, but we're going to be working with the radii of the gears and such here for our mechanical advantage. And one other massive machine that we kind of forget to look about, or forget to look into, is the human body. Okay, so I know we have muscles and it all works biologically, but there's actually mechanics involved to the human body. And we kind of understand our own body mechanics to make forces easier, or make things easier for us based on our body size. It's a bunch of levers. Talk about football players and them getting their leverage on the football or on the line. Okay, so linemen really got to understand leverage. Thinking of what I did, shot put, discus, hammer, I really have to understand leverage. I have to understand body mechanics, otherwise I'm not going to be the best athlete. Okay, so components of our body include several of these things: a bar, a source of force, a fulcrum or pivot point. So this is a lot in our body. And a resistance. So if you think about every muscle in our body, we have pairs of muscles. You're going to have a muscle that squeezes to extend and squeezes to contract. Okay, so they come in force pairs in our muscles as well. Okay. Lever systems of the human body are complex. They're not very efficient and have low mechanical advantages, just because if you look at all the different components involved, there's little joints and everything everywhere. If we had a rigid bar, it might work better, but we might not be able to move very well. It might be moving like a robot. All right, let's look at an example here. So you examine the rear wheel on your bicycle has a radius of 35.6 centimeters. So we'll say radius of wheel. We're going to write these down. 35.6 centimeters. And a gear with a radius of 4 centimeters. So radius of gear is 4 centimeters. When the chain is pulled, so this is our effort force, at 155 newtons, the wheel rim moves 14 centimeters. So that's going to be our resistance distance, okay, because that is, if we look here, that's what's moving, okay. The wheel is moving on the ground. So that would be the final outcome, which is going to be our resistance distance, and it is 14.0 centimeters. And our efficiency is given at 95%. And remember, like I mentioned before, you can have 0.95 or 95% if you want to. So A, what is the ideal mechanical advantage of the wheel and gear? Okay, so this is where we kind of have to identify effort, forces, and such involved. So ideal mechanical advantage is going to be like an effort force or effort radius. Okay, so we'll make this, we'll make it an effort radius. So radius effort over radius resistance. And we got a couple things going on here because we're pulling on a chain. So that chain has to have some sort of a effort force right there. So you can see that we'll just kind of have that as radius of chain or something like that. And then that's going to be the radius of the gear that we're working on. Since that's connected to the wheel, that's our little axle, right? Our wheel, we're going to have the radius of the gear is going to turn the wheel, so radius of the wheel. And since we're specifically looking at the wheel and gear, we aren't going to take into consideration that pull of the chain, so we don't need that part, and we can kind of look at this portion here. So to get our ideal mechanical advantage, we need a radius of the gear, which is 4.0 centimeters, over the radius of the wheel, which is 35.6 centimeters. And you go ahead and divide those numbers, and we get a value of 0.112. So that's our ideal mechanical advantage. For part B, we need to calculate the mechanical advantage of the wheel. Okay, so we know, if we kind of look at this equation, we know an effort force, but we don't know a resistant force. We don't know the force on the ground. So we're going to be using this one since we do know an efficiency. Okay, and so again, remember, if we put this in as 0.95, we don't really need that portion. So 0.95 is my efficiency, and my mechanical advantage, I don't know yet, but I'll calculate it, and my ideal mechanical advantage is 0.112. So some simple math there, multiply by 0.112 on both sides, and we get a mechanical advantage of 0.107. Okay. So now C, we can kind of work to calculate the resistance force. So we can use our mechanical advantage and our forces involved here. So our mechanical advantage is 0.107. We don't know our resistance force. We can find that. We know our effort force is 155 newtons. Okay, so again, a little simple math here. Multiply by 155 newtons. And we get a resistance force of 16.54 newtons. And then the final question here, how far was the chain pulled to move the rim 14 centimeters? So with that one, we can use our ideal mechanical advantage. Okay, we want to figure out the distance of the small gear to get the wheel to move a certain distance. So our ideal mechanical advantage is 0.112. It's going to be equal to our effort distance, which we don't know that. That's what we're trying to figure out over our resistance distance. So that was the wheel moving on the ground. We can figure that out. So our effort distance, that would be how far the inner gear moves, is 1.57 centimeters. So quite a bit of information going on in this problem. You have to kind of see how they're all connected, and it's much simpler if you have these sitting in front of you. But starting off with the ideal mechanical advantage, you have to understand what is your effort radius versus your resistant radius. So let's take a look at a problem down here. Let's move it up a little bit. So a bicycle has a pedal radius of 15 centimeters, the front gear radius of 5.57 centimeters, and a rear gear radius of 4 centimeters, and a rear wheel radius of 35.6 centimeters. What's the ideal mechanical advantage of the bicycle? Okay, so now we're talking about the pedals. Pedal radius of that, front gear radius of that, a rear gear radius of that, and a rear wheel radius of that. So again, we got to figure out our effort and our resistance. So we're going to make ratios here. So we do, let's say our radius of pedals, and I wrote this on the last slide. That's going to be our effort radius over the radius of the gear, and this is our resistance. Okay, so this will be, our front gear will be connected to the rear gear. Okay, so the radius of the rear gear over the rear radius of the rear wheel. So you can see with our compound machine here, we have to have all of this information, okay? And we can throw everything in there. Now, sometimes it might be better to organize it where you have the gears together, then the pedal and the wheel together. So we would have the rear gear over the front gear. Okay, so our rear gear is 4.0 centimeters, and the front gear is 5.57 centimeters. And then we have our pedals and wheels. So pedal is 15 centimeters, and the wheel is 35.6 centimeters. You go ahead and multiply those out, and you will get your ideal mechanical advantage. Which is about 0.30. Okay, now you can use this information, all this stuff as well. Say we want to figure out if one of the gears is going to turn one time. Okay, so let's say our front gear turns one full revolution. Okay, how many times is the smaller one going to turn? So this is kind of a common sense type question. So our front gear is going to cover 5.57 centimeters, whereas the rear gear is going to cover 4.0 centimeters. So you can just multiply those, or excuse me, divide those two to figure out how many times one is going to turn. So obviously the smaller one is going to turn more than the larger one. So if we went one complete revolution with the larger gear, we could divide those to figure out how many times the smaller one would rotate, which would be, in this scenario, 1.39 times. So the smaller gear would rotate 1.39 times compared to the larger gear. So your assignment will be the questions in the textbook. I want you guys to try to work through these. I might make an answer key for these, and I can leave my teacher's textbook in the front of the classroom for you guys to look through these. But I might try to make a video working through these if I have time. But you need to work from 54 through 63, and we can kind of look through these when I get back to help out. Okay, and then on top of that, you have a Module 9 and 10 worksheet. This one here is going to be probably quite a bit easier than these. Okay, because I know that these mechanical advantages and stuff like that can be kind of confusing at times. But you have these two assignments to work on. And then tomorrow we will be doing a lab. So we can look at some of these questions if we need to, and then we're going to work through the lab. Okay? Thanks for watching. Have a good rest of your day.